I'm going to talk to you about population structure and complexity in high channel multitask recordings. It's not the sexiest title, but I wanted to make sure you know that there is a good reason for this to be in a foundation model workshop, and I'll definitely share some thoughts on foundation models specifically for BCI applications. So quick disclosure, I'm on sabbatical right now from Emory and Georgia Tech, so I'm actually a research scientist at Meta with David's team and Adam and others. But Meta has nothing to do with this up, just letting you know that I have that. Great. Okay, so when we talk about foundation models, in general, I mean, I think there's a ton of excitement and for a variety of applications, but one of the applications we think a lot about is, can they help BCIs? So if we think about how foundation models can be useful for BCIs, where might improvements come from? So one place is that they could be useful for identifying patterns in noisy data, right? Like if you see enough diverse data, then you can be really good at denoising it. So this might be kind of just good feature extraction. Um, on the other side, kind of at the output side, if you think about the downstream task of, let's say we're talking about handwriting, we want to be able to separate out individual characters, but we also want to learn individual writing styles, right? So we can get a lot from seeing diverse data and being able to recognize kind of per user variability, but also shared structure in the task itself. So this is kind of like on the input side, maybe on the output side, maybe, but I think maybe one of the things we're potentially most excited about is the idea that there are shared neural dynamics across in brains, right? Across sessions, contexts, tasks, modalities, subjects, and species. And so we've seen that, some really exciting work in the last couple of years that foundation models can be used to slurp up diverse data. I think Poyo is a great example where they trained on with monkeys, reaching tasks in a variety of configurations, like vertical, horizontal, etc. Joel, now that he's free of the shackles of his old advisor, has shown that you can go out to like trillions of parameters and do some really cool stuff with scaling with NDT 2 and 3. And now we've got multi-session, we've got multi-species, right? We've got downstream targets like kinematics, EMG, forces. And there's a lot of good examples. MTM also showing that you can slurp up IBL data from many different brain areas and many mice. And what I think is most exciting is that we're starting to see ways, uh, uh, maybe principled ways of integrating these very, very different data. And that's really cool. So when we think about how these methods can be useful for learning shared dynamics, well, first, like, is there evidence for shared dynamics? And I think there's substantial evidence for shared dynamics across subjects and species. And here I'm thinking about, there's plenty of work in this domain, but some great work from Churchland and Cunningham showing that across many different monkeys, you see the same kind of consistent underlying dynamical structure during reaches. We extended this to people with paralysis and showed the same thing, that you see very consistent shared structure. Juan and colleagues have done some great work recently showing that you can align using supervised alignment across subjects. Similarly, we believe there's shared dynamics across sessions, right? So in the LFADS paper, we showed that you can align data spanning 5 months and improve decoding from separate recordings across 5 months and improve decoding on any individual session. Similarly, Juan did some great analysis with supervised alignment to show that you can maintain stable decoding by aligning latent dynamics across years. So that's really exciting. And building on that, there's been a lot of recent work on unsupervised methods to align latent dynamics so that we can keep BCIs more stable. And then there's also the interesting question of, are there shared dynamics across contexts, tasks, and modalities? And Juan has done some great work in this space. I wanted to shout out some great work by Frank Willett and Daryl Dio because it's specifically very relevant to BCI, showing that as subjects make movements, if they attempt the same movement, let's say with their right hand or their left hand or their right foot or their left foot, right, very different, physical effectors. At the course level, we see a lot of shared structure in the neural activity itself, which gives us hope that there's something for these models to latch onto when we're trying to decode. Okay, so the couple segments of my talk towards foundation models for BCIs, I want to talk about what we call modality invariant signatures of intention in motor cortex. And hopefully you guys can think about how we might leverage these for foundation models for BCIs. And then I'll spend the last couple slides talking about, it's been shouted out a couple times already, a new BCI-centric evaluation platform for models. So multitask, multi-subject, multi-species. I think this is a great way to evaluate models for BCI applications. Okay, so as I mentioned, there's a few different ways there could be shared dynamics in the brain. And let's dial in specifically on this idea of shared dynamics across contexts and tasks. So we know there's a lot of behavioral evidence for the idea that there's some shared underlying system for motor control that transfers across modalities, right? So if you write something, you have some sort of stereotyped handwriting when you write with your hand. But if you write, by holding your arm out, if you write with your left hand, if you write with your head movements or foot movements, you actually see kind of signatures of that same underlying handwriting, which says that there's something likely shared across these modalities. And in that paper I mentioned with Frank and Daryl, they talked about this idea of kind of a compositional structure for control. And I'm abstracting away a little bit of what they propose. But the idea is like if you have motor cortex and it's trying to control, let's say your right hand, your left hand, your right arm, your left arm, etc., then it's to some degree there are inputs to the system that there's like an abstract movement pattern or movement intention target. And then maybe some inputs that tell you, should this be on the left or right side? Should this be an arm versus hand? And the idea is that, the system kind of integrates this abstract intentional goal with kind of the context of what effectors should be used to produce kind of the right muscle output, right? So if you want right hand for this pattern, the system will produce an output that way. If you switched one of these inputs potentially, the system would produce a different output. So going from right hand to right arm, let's say, to make the same type of movement. So key takeaways of this part of the talk, I'm not going to belabor the points. We find modality independent, intention-related signals in neural population activity. And we see that information flows on millisecond timescales between these modality-independent and modality-specific systems. Yeah, and with high channel count recordings, we can resolve these patterns on a single trial basis and on a millisecond timescale. So I want to definitely shout out the people that really did this work. I don't do anything anymore except poke people to give me figures. But this work is led by Mattia Rigatti, grad student in my lab, and Anjali Agarwal, another grad student in my lab. Brianna and Felix also participated. And this is also a collaboration with some folks at Neuralink, especially Robert Sutherland and Nir Evan Chen. Okay, so in this work, we're looking at intracortical recordings from two monkeys, again, in collaboration with Neuralink. So if you're familiar with the Neuralink implant, so the monkeys are at Neuralink, not at Emory. If you're familiar with the Neuralink N1 implant, they're threads, and each thread has multiple electrodes along a thread. So we're looking at monkey brains. Uh, I don't know if this is an anatomy crowd, but central sulcus is the thing on the right. Anterior to that is the precentral gyrus. That's where motor cortex, primary motor cortex, premotor cortex, hopefully you've heard these words before, that's where they're situated. And so these dots tell you where these threads are implanted. So they're, again, 1024 total electrodes, which means 128 implant sites and then 8 electrodes along the threads themselves. Okay, so you can kind of see on the right a spatial map that shows, kind of, area and depth as well. Okay, with these recordings, the folks at Neuralink were kind enough to train monkeys to perform the same dexterous, high precision cursor control task under different modalities. So you guys have seen random target-like tasks before. This is a pretty high precision task. It's a 35 by 35 grid, so you have to be pretty precise to stop on these targets. So it's really kind of pushing the system from the BCI standpoint, we think about bit rates. This is how you get to really high bit rates, by getting to really high precision control. Okay, the monkeys did this task either by controlling a joystick, or by controlling, they actually trained their monkeys to control a literal computer mouse, like, I don't know, Best Buy or something like that. So, you can think about the different movements that are involved here, wrist movements for the joystick versus whole arm movements for the mouse. And then they also trained a BCI decoder based on the joystick activity. And that's another kind of modality here, where monkeys controlled the cursor, the same task, but with the BCI decoder rather than either of these two physical effectors. And these are collected across several days. We have thousands of trials of each modality. Okay, so let me give you a sense of what the data look like. So sorry that this is in the way. We have binned threshold crossings, binned at 15 milliseconds. That's the natural way the data come off the device. And so on the top are the kind of binned spiking that we get. I've eliminated a lot of low firing rate channels, but we end up with about 567 good channels. And we take that activity, and we can take the continuous bin spiking activity and denoise it using auto LFADs. If you're not familiar, maybe questions at the end if you don't mind. We'll get kind of denoised firing rates on kind of millisecond timescales by sending this through auto LFADs, and we can do this on the continuous data stream, so we don't have to worry about trial structure or those sorts of assumptions. Okay, so the first question we want to ask here is, how consistent is neural activity when performing the same task under different, that should say control modalities, but people in the room can't see that, control modalities. So same task. In this case, all right, we're going to do some old school analyses. I know we're not supposed to do that anymore because we're supposed to throw everything into a black box, but we're going to look at responses for just a little bit, and then I promise we won't look at them anymore. Okay. We're going to group trials by movement direction, so the color is going to represent what angle the next target is in. And so, here's an example for monkey H for channel 563. Average firing rates as you go to green here, it is a specific direction, and you see that the channel modulates a lot. And it does basically the same thing, whether the monkey's controlling, with the mouse or controlling with the joystick. So this is very consistent tuning. Here's another example of very consistent tuning, where kind of the tuning properties are preserved. But here's an example, same monkey, same two tasks, where tuning basically flips completely, depending on whether it's a joystick or mouse. And I don't think this surprises anybody. We know that the brain does a lot of stuff, and maybe a single neuron's tuning is not an indication of everything the brain is doing. But we just wanted to get grounded in the data, so we quantify kind of the change in preferred direction between tasks. And what I'm just showing you here is that kind of the consistency in tuning for a given channel on across the brain, basically. And just key point here is there's a lot of consistency and there's a lot of variability across channels. There's a lot of heterogeneity here. We've done a lot of analyses to say, like, okay, is it localized in space? Is it localized in depth? I'm not going to show you those, just to say that we're kind of scratching our heads at the lack of spatial organization here. Okay. All right, single channels, we don't do that anymore. Okay, so forget about that. Now, at the population level, we want to ask, is there a prevalent subspace of activity that is shared across modalities? So now linear algebra, I think that's still okay for another couple of months. Is that right? Or okay. We're gonna try to decompose population activity into subspaces. So we're going to try to find a subspace that's shared across tasks, and then subspaces that are specific to the, I'm sorry, I say tasks, modality, so specific to the modality of control. And you could imagine that, activity may kind of evolve preferentially in one subspace first, like the shared subspace, and then transition into the more modality-specific subspaces over time. Okay, so we're going to do this. This is the simple linear methods, as I mentioned, and we're going to do an optimization that Brian de Cleva introduced, where we take neural activity, we decompose it into these orthogonal subspaces. So one of these would be shared, and then one subspace per modality that we're interested in. So for example, we might find a joystick subspace, a mouse subspace, BCI subspace, etc., and shared activity here. I'll just note, and this is important for basically everything else, that this decomposition is unsupervised with respect to movement direction. So you're only telling the optimization kind of what context is being performed or modality is being performed at any time, but not, anything about the animal's actual movements. And so what we see, so I'm just going to break down kind of the joystick trials for a second. Um, this is these are different dimensions, and each bar represents the variance of those dimensions. So sorted by decreasing variance. And what you see is that the first few dimensions, the majority of the variance, like about 56%, is shared. So that kind of shared activity is a very, very large component of the neural activity. There is some activity that's joystick specific. Those are those red bars. And partially shared just means there's some overlap with stuff with dimensions that are used for other modalities as well. Okay, so we see for joystick, for mouse, for BCI, that in all cases, the largest components of activity are these shared. So, more than 50% of the activity is shared across modalities. And then each modality has these kind of specific dimensions as well. And of course, this is just, obviously a linear analysis, but maybe one of the things that was surprising to me was how clean these analyses come out, which I'll show you, which may be kind of as you scale to higher and higher dimensions, linear analyses may be more useful, but reserve judgment on that. Okay, so is there, prevalent subspace of activity that's shared across modalities? I think that the last thing said yes, but let's see what that actually looks like. So we're going to look at that shared subspace and a little bit of systems neuro here. So we're going to take individual trials. We're going to figure out when the monkey starts to move by computing a movement onset. And we're going to look specifically in the window of time around that movement onset. So we're looking 300 milliseconds before movement is detectable to 300 milliseconds after movement is detectable. Okay, so the key thing is, this is what we see in that shared subspace. So these are neural population trajectories in that shared subspace alone, colored by the direction that the monkey is moving in, right? In that negative 300 to 300 period. So the key thing I want to show you here, if I can play that video again. I did something funny with build, sorry. Key thing I want to show you is that build. Okay, here. It's pretty hard to tell, but there are trials for all three modalities here. What you see is really consistent coloring, like depending on the which direction the monkey is moving in, you see that trajectories are grouped. But there are also markers for the different modalities, but it's very hard to see that because they're all basically overlapping. In this shared subspace, it's very, very hard to distinguish between which modality was being used for control. Even though there was, there's no alignment here to try to kind of line up directions and stuff like that. It's just, if you're going to move up and to the right, you're going to follow this trajectory in the shared subspace, regardless of which modality is being controlled. Okay, and then we find that there are also these modality-specific subspaces, so joystick, mouse, and BCI. And I'll just show you kind of trajectories for those as well. And it's kind of what you expect, these trajectories seem to be diverge based on what direction the monkey is moving in. But I think the key thing, and when I mentioned like linear analyses work really well on these recordings, the key thing is those gray dots, which are like for the joystick subspace, the non-joystick trials, right? So what does mouse look like in the joystick subspace? What does BCI look like in the joystick subspace? It doesn't look like anything. It's basically null, right? In these specific subspaces. So surprisingly, this activity does seem to kind of separate out really cleanly in these high dimensional recordings. Sure, yeah. Except for the builds. Yeah. So The key takeaway here is that trajectories are organized by reaching direction. It's very hard to compare like any specific dimensions here because they're just different subspaces. It would be kind of meaningless to compare the different dimensions themselves. Okay, so if we think about this idea, then going back to this idea of compositional control, it's an idea that there's some kind of modality independent movement intention, and that's kind of on the left side here, and that needs to get translated to the modality specific command to move the right effector, the correct effector. So if that's the case, you would probably expect to see kind of some temporal separation here where the kind of higher level intentional signal should be seen first before kind of the specific signals. So now we're going to look at that same window around movement onset, but we're going to really dial in to a specific period. So 150 before to 100 after. These are in milliseconds. And I'm going to play these videos. These are only joystick trials. The top is the shared subspace. So joystick trials projected in the shared subspace. The bottom is joystick trials projected into the joystick specific subspace. Okay. And so the video pauses at -150. You see things are pretty much overlapping, and then pauses again at 100 after movement onset. Okay. That's just to orient you. I'll play it again. But the key thing I want you to see, just visually, is that in the shared subspace, things are already kind of starting to collapse around 100 milliseconds after movement onset. Whereas in the specific subspace, that's kind of the peak of the activity. What I'm trying to get across here is there's like a temporal offset to when things happen, whether you're in the shared subspace or the specific subspace. Things seem to occur first in shared and then move to the specific subspaces. So I'll just play that again. So pay specific attention to what happens right now. Things go out, and on the top, they're collapsing already. On the bottom, it's still kind of the peak of the expansion, meaning things are happening kind of later on the bottom in that joystick specific subspace. And, we wanted to quantify this. Do we see information flow from the shared subspace modality to the modality specific subspaces? We do this with a method, delayed latent across groups. Avery in Byron's group came up with this, and it's really been wonderful. Originally applied to think about multi-area recording, so looking at flow between area A and area B. We are slightly adapting that to just think about flow between subspace A and subspace B. And when we apply that, so I'm just going to unpack this for a little bit. So if you look at kind of shared to any of the specific subspaces, so shared to mouse or shared to joystick, you see that DLAG estimates that there are shared signal flow, and there's a latency there of about 10 to 15 milliseconds or something like that between the shared subspace and these specific subspaces. To control, just in case this is random fluctuation, we looked at like if you just took a specific subspace and tried to do the same thing, we don't see any kind of significant bias here in what's estimated, which tells us that there's some pretty strong evidence that we are seeing kind of information flow from this, what we think is a higher level kind of intentional signal to those modality specific subspaces. Okay, another prediction, if this model is correct, that information is flowing between subspaces, is that if you look at when the monkey is making a corrective movement, we might see that first at the abstract level before it gets translated into the effector specific or modality specific level. Because the monkey is doing this task, it's seeing visual feedback, it has to understand, did I make a mistake? How do I correct? And that's kind of all in task space, but then the corrections themselves have to happen in depending on differently depending on the modality that the monkey's using. So just as an example, I'm showing you a bunch of it's a hard analysis. So we had to isolate a bunch of individual trials. These are examples of very straight trials. And we found examples where the monkey was making corrective movements. So that would look something like this, where it's initially straight, and you see there's kind of like a hard turn there, right? So an indication that there's a direction change and the monkey makes a movement. I'm not going to go into this too much, but what we see is that the differences, so when can you detect that the monkey is correcting? That always happens first in the shared subspace before it happens in the modality-specific subspace. Okay, so some key takeaways here. Modality-independent intention-related signals can be resolved on millisecond timescales. These could be a great substrate for a foundation model-based BCI, right? Because this is something that we can latch onto that's like really related to intention. But we also have to be really careful about this because as BCIs become more capable, we may not always want to collapse down, right? We may want to know, are you trying to move your right hand or right wrist? So sometimes we want to maintain differences. I don't have time to go into this, but I want to highlight some recent work from Aaron Kuntz and Benjamin Meshad-Krasa at Stanford, showing that the same type of structure exists when subjects are attempting to speak versus when they have inner thoughts. We see a lot of shared activity between those two contexts. And that's absolutely a case where you don't want a BCI to collapse, right? You don't want to just decode the same thing regardless of whether the subject is attempting to speak versus inner thoughts. Otherwise, you just be broadcasting their inner thoughts all the time. So we have to be really careful, right, about how our models treat this activity and ensure they're not kind of collapsing things down, but rather there's a lot of reason to preserve. And we need to evaluate our models with the downstream task in mind. I don't think I have a ton of time to talk about few shot algorithms for consistent decoding. So I'm just gonna leave it up with if I can look through, I shouldn't use so many filters. Key point was neural latency benchmark, great for representation, evaluating representations, not great for decoding. If you are interested in thinking about how your models work for decoding, we've got a lot of different species, we've got a lot of different tasks that are all kind of BCI centric. We think about held out evaluation, we've got few shot training data. This is kind of the types of evaluation we want to ensure that these models are going to work well for BCI. So ways to test generalization of foundation models. Bro, can you even zero shot? There's a lot of good other things here to think about, multitask, multi-species, etc. But I just want to acknowledge the key people that did the work. Falcon, thanks very much.